Now, this disc is a mid-range disc. It has a glide number of 4, which is the second number right here. 5 would be the speed, 0 would be the turn, and 3 would be the fade, which I won't explain because it'll take a while and it doesn't really relate to math. Or it does probably, but we're talking about glide today. This disc with a number of 4 is meant more for controlled shots that don't go too far. So as you'll see, this one will fall in the air much quicker than something with a higher glide, like the next disc has. Now, this disc right here is a distance driver, and as you can see right here, the number for the glide is higher than the mid-range, making it fly in the air longer, because in general it wants to stay in the air longer than the mid-range does. So this is how this one flies. Alright, now this is where the math comes into play as far as the disc's flight is concerned. So we see here the lift force applied to the disc is equal to 1/2 of the density times velocity squared times area times drag coefficient. Now, both of these discs will have the same drag coefficient, roughly, because the drag coefficient on a frisbee is nearly identical to the drag coefficient of an airplane's wing, and that is because these achieve lift in the same way. They're curved on top so that the air traveling over the top of the disc is moving faster than the air traveling below the disc. As far as the area is concerned, that will also be the same. Both of these discs are PDGA approved, meaning that they are at regulation size, and therefore, as you can see here, they're almost identical as far as diameter is concerned, and area too is with the thickness. Now, the velocity and the density are the two factors here that actually have an important effect on the disc's lift force. As we can see here, this distance driver has a speed rating of 11, meaning that in optimal flying conditions, it'll be traveling at a much faster velocity than a disc like this that has a speed rating of only 5. So yeah, that affects it quite a bit. And the density. As you can see here, this disc has a really thick ring around the edge. It's got much more plastic, and it's much more dense than this disc right here, which only has a thin ring around the edge that isn't nearly as thick or wide as the one on the distance driver. So with an increase in density and velocity, that translates to a much larger lift force. As an add-on to our Can We Math This video, I'm including a demonstration of the disc grabber, which you will see in a moment. Typically, when a disc golf disc goes over the fence, as this one has right here, we would use these tape measures to slide it out and kind of grab it, pull it back in. And it works, but the little grabber here at the end is really narrow, so it'll slip off the left and right side of the disc. And it takes a while. It works, but not as easy as it does with the disc grabber. And here's what it looks like without. As you can see, you have to get the balance on it just right to have it not slip off one way or the other. So, not quite as easy as it is with the disc grabber. Now here is the same operation completed with the attached disc grabber. Just like that, and as you can see, it is not slipping off to one side or the other. And it's still not super easy, but it's easier than it would be without it. like that.